Hi, I'm Ken. I work in Applications Engineering here at Corning Cable Systems. This Corning tutorial explains basic considerations for selecting a particular multimode fiber. Those considerations are mostly driven by the particular link protocol and the distance required. This tutorial steps back a bit to explain, in layman's terms, what multimode fiber bandwidth is, questions you should understand about varying ways to measure that bandwidth, and how to be sure you get what you need with multimode fiber. This animation shows several propagating modes in a step index multimode fiber. Because of the step index profile, refraction occurs only at the core clad boundary. As you can see, light propagating along different paths travels greater or lesser distances from one end of the fiber to the other, and because of the step index, all of the energy propagates at the same speed. The result is that different modes arrive at the far end of the fiber at slightly differing times, and those time differences grow as the fiber length increases. These time differences are called differential modal delay, sometimes just DMD. Let's look at how fiber manufacturers minimize differential modal delays. This animation shows a graded index multimode fiber. That means the refractive index of the core changes continuously from the center line to the core clad boundary. Just as in the previous animation, light propagates along several paths. For clarity, we're showing only two. But differing from the earlier animation, the graded index profile minimizes time delays between modes. Light following longer paths propagates more quickly, and light following more direct paths propagates more slowly. Minimizing the time differences, that is, the differential modal delays, is the goal of fiber manufacturers. This is because differential modal delay causes received pulses to spread out in time. If a pulse spreads enough, either the receiver no longer can distinguish a digital 1 from a 0, or a pulse bleeds into pulses sent before or after it. Look back to our first example. A technician might measure the delay between the slowest mode and the fastest mode on this particular length of fiber, let's say 5 picoseconds. Another technician, measuring a different fiber, maybe a different length, could measure an average delay between the 5 widest spread modes in that fiber as 4.5 picoseconds. So, which of those fibers is higher performance? Just knowing some partial information about absolute differential modal delays is not terribly useful. With only the information we just heard, deciding which of those two fibers is better is not possible. Worse, a designer or technician can't tell whether either of them is good enough for that new fiber channel RFQ that showed up this morning, or even whether both of them are overkill and will cost too much for that job. What we need is a standard measurement. Bandwidth is simply the fast Fourier transform of the input pulse, taking the bandwidth as the -3 decibel or half power frequency. Okay, this is how bandwidth is determined, but what does it mean? In a nutshell, bandwidth is simply a measure of how square the input step or pulse remains, and for how far down the fiber. Now that is a useful bit of information. Look at this bit of the graphic though. Bandwidth, that is, preserving the pulse shape, depends on both modal delays, we just talked about that, that's determined by the fiber, and the modal powers. That's not determined by the fiber, but by the transmitter. Let's talk about the possible modal power scenarios. You'll probably recall that 850 nanometer systems operate almost exclusively using lasers, and usually with vertical cavity surface emitting lasers, commonly called VCSELs. You'll probably recall too that VCSEL spot sizes, typically 8 microns, are far smaller than 50 micron multimode fiber cores, so obviously a VCSEL could be launching just about anywhere in that relatively big core. And on top of that, VCSELs can be hot inside or outside or on one side. Given all that possible variation, we still need a useful way to compare one fiber to another with whatever VCSEL a transmitter might contain, and regardless of which manufacturer made the fiber. There are a couple of options. We could scan a VCSEL across a fiber and directly measure the differential modal delay. Standards describe 6 different masks or acceptable templates for the result. The drawbacks of such a method are DMD masks are only pass-fail measurements. These pass-fail measurements simply do not directly correlate to bandwidth or to link distance limits, and you can't scale these results. That is, you can't extrapolate a measurement made on a 200-meter fiber to a 500-meter fiber. Finally, passing any of 6 prescribed masks means a fiber passes the bandwidth test. This seems like a shaky proposition to bet your company's reputation. There is a better way to compare fibers. Corning measures differential modal delay using several VCSEL sources, chosen to check at the extremes of the allowable laser sources. This slide shows the difference in just 2 different VCSELs. Several more results, using widely varying VCSELs, are combined to calculate the minimum modal bandwidth of this fiber using any possible standards-compliant VCSEL. This is called Calculated Minimum Effective Modal Bandwidth, or min-EMBC. In short, with DMD masks, you buy a go, no-go checked fiber that can, usually will, meet the stated bandwidth. With minimum effective modal bandwidth, you will buy a fiber that will meet or exceed the stated bandwidth with any standards compliant VCSEL. A higher bandwidth fiber does a better job of getting all the modes to the receiver at the same time. The practical measurement for comparing one fiber's differential modal delay to another fiber's differential modal delay is called bandwidth. Higher bandwidth preserves the transmitted pulse better, improving the receiver's accuracy in discerning ones from zeros. That is, minimizing the bit error rate. The superior method for measuring bandwidth is calculated minimum effective modal bandwidth, min-EMBC. Min-EMBC is standards compliant. Min-EMBC is more conservative than DMD masks. Corning's laser optimized multimode fiber is always min-EMBC characterized. Which fiber and bandwidth bucket to choose is as simple as comparing your link protocol and distance to this table. That's it. Sorry for sliding off into mathematics land for one slide, but if you have a question, call us or send us an email at cablesystems@corning.com. Corning Cable Systems always recommends getting trained in fiber optic installation. Please remember to follow all safety rules and procedures when working with fiber. We offer a series of classes that can help you. Thank you.